Thank you very much, and thank you for coming. This is always a pleasure to speak at LCA, and I'm always intimidated by the quality of stuff, and I have learned this year that the worst part about going on the last day is you see so many great talks throughout the week, and then I'm like, what in the world am I doing here? So yeah, I'm feeling a little bit of extra pressure. Also had the special privilege, my wife got to fly in and is here today too, so that's just extra pressure there. So that being said, my name is John Dickinson, and for the past 9 years or so, I've been working on a project called OpenStack Swift. It's an object storage system, and you can conceptually think about it like Amazon S3, except that it's open source, and you can deploy it in your own data center, and it's pretty great, and it's used all over the world, and I love it. 1space is what I am talking about today, and 1space is a project that is built alongside of or on top of Swift, and it is designed to, well, we'll get into what all it does, but it is as well an open source project, and so one of the reasons to talk about it here today is to say you should use it, you should come contribute to it, you should come check it out. So let's dive in. The problem, like why are we here? What's the whole thing that needs fixing that OneSpace can fix? And the problem is that we have got data everywhere. And I myself have been part of trying to tell the story that when you deploy your apps, you just should put it all in object storage like Swift and build all your apps to talk to that centralized data storage thing. And that's a great story, and it really helps facilitate making applications and making them easier to use and all that kind of stuff. But the world's a lot messier than that, and you can have one group inside of a company that is building things off of, in a whole brand new way, and they're using object storage. You've got other people over here who are writing stuff to databases. You've got other people over here who are like, we're our own new team. We're going to do everything in Amazon, and we're going to do it all over there. And so what you end up with is a lot of applications running in a lot of different places, talking to a lot of different storage systems. And the company in general, or the larger organization, looks at it and says, we've got a mess on our hands. How do we fix this? And it's not helped by the fact that every few years recently, we as an industry have been telling application developers a new way to write programs. So I'm going to build a real big fast program on my bare metal, VM, containers. Wait, we're going to do like functions as a service sort of thing now. So rewrite all your apps and do whole different things. And the truth is that there are great reasons to write different apps in different ways, but each of these ways you would write an app generally have a way to store data that is naturally best for it. Like, for example, if you're going to go write it in some sort of holistic cloud infrastructure, you're probably going to use the storage that's there. But if you're going to write it that's just on you've got access to a single machine, you're probably going to write it as if it's running off of a local bare metal or VM box. So the point is, we get a lot of different data in a lot of different places. And it's not just the fact that we've got applications running in different places in different ways. The problem, unfortunately, is that we've got a huge amount of proliferation in ways to write apps in places where they're being written, but not a huge amount of proliferation in the options that people have when they're starting to do cloud infrastructure. The reality is that there's a few huge providers that are dominating the industry. And then when somebody says, I'm going to build something that's going to run on more than one machine, and I'm going to start putting it into some sort of scale-out infrastructure, they're basically going to write that to put it in Amazon or Google or Microsoft. Or if you're not in the whole Western culture sort of thing, there's a couple big providers in China that are basically taking over the industry at this point. And then there's a few other things out there, and that's normally where the open source world has kind of played in this. And I've been a part of that with OpenStack for the past nearly decade. And it's become the fact that we used to say we're gonna provide this this big open source infrastructure, cloud infrastructure for people to use, and that's wonderful. And I think that has to happen, and people should be using that. But when we started that back in 2010, 2009, and that kind of era, the industry looked very different than it looks now. And now the idea of somebody coming along and building something new and saying we're going to whole cloth replace these companies that are investing billions of dollars a quarter in their infrastructure is something that is not really a great, logical, smart step to take right now. So that's the kind of problem of where we are. We've told people to consolidate, and they haven't. We've told people to use cloud infrastructure, and they did, but it wasn't something that it was common. It was a few different siloed cloud providers. So how do we tie that back together? And how do we, again, give people the ability to free their data and have control and ownership over their data? If you've heard anything else I've ever talked about with Swift, you know that that's a big thing for me, is the reason that these things are important and important to be open source, and it's a huge theme at every LCA I've been to, is that people should be in control of their own data and have control over where it goes, how they deal with it, who has access to it, and the best way to do that is with open source. So we've got this reality of a lot of different things in a lot of different places. So let's specifically talk about some of those specific use cases and problems that people have, given this whole mismatch of things. The first one is one of my favorite ones, and it's discussions with some people had this use case, and it's kind of where the idea of 1space, as I know it, first came from. And that idea is that I've got my own cloud infrastructure, compute and storage. I put all this stuff in my storage. I mutate it or compute on it with the compute, and that's good. But you look at the costs of running your compute, of moving the data back and forth, of where the data is stored, and you realize that you can use compute in public cloud in the middle of the night for dirt cheap. And when it comes to, say, doing a lot of special effects rendering, movie animation rendering, analytics for large data sets, things like that, it almost would be, it's a bad idea to not take advantage of that. But if you're going to write the next great self-driving car neural network sort of thing, and you'd have to process all of your data, and you want to push it out a little bit into a public cloud, that data is really important. You don't want to give it all away necessarily. Same thing with your movie assets or anything like that. So how do you give access? How do you allow that data to be computed in the public cloud while still keeping majority of your data and all the results in your on-premises cloud? This one is pretty exciting to me because it's the first sort of use case idea where people used to, if you remember, talk about the whole cloud bursting sort of thing. Is I've got some computers here, I've got some computers over there, and when demand scales up past a certain point, I'm going to start using that over there, and that's kind of great. And it makes sense for compute, but it never makes sense for storage. Until we started thinking about this, and it's really kind of the first idea of giving access between this public and private cloud storage that wasn't immediately laughable when I first heard it. The other, another kind of use case you'll hear about a lot is just the old common use case of it's expensive to use somebody else's infrastructure, so I want to spend less money. So how do I use my own infrastructure? So you want to move your data from a public cloud because they're charging you lots of money, and you want to bring it back to your on-premises cloud because you can save money doing that. One of the advantages of a lot of cloud infrastructure is it allows you to start separating the applications from the infrastructure that's on it. And so you have application developers who are writing their apps. You have the sysadmins who are actually keeping everything up and running. And they're decoupled so that you don't have to necessarily have a strong degree of coordination between the two. So think about this. If you're going to migrate everything, for example, from Amazon back to your own in-house storage, you don't want to turn off all of your applications for a week or more to move a few petabytes of data out of S3 onto your own hard drives. That is just something you can't do. So you need to have your apps. You want them to continue to keep working, but you want your admins to be able to migrate the data back and forth based on whatever schedule is up to them. So this use case of being able to do a live migration between two different clouds, like your on-premises cloud and a public cloud, without having to rewrite your apps to talk to different APIs, without having to turn off all of your apps during this migration, it's something that many people struggle with and wonder how to solve. Another sort of use case is that I want to keep all of my recent data local, and I want to archive it someplace else. And maybe I want to archive it after 30 days and only keep the last month's worth of data locally. Or I want to keep the I just only want to build out my on-premises cluster to be a certain size, just maybe say a few petabytes. I don't want to put anything bigger than that. I want to put it someplace else because I can offload that, store it more cheaply, potentially, or something like that. But if you do that, then how do you get access to that stuff that's remote? How can you transparently just read all that back? How can you unify those two things? It's one of the other ideas that was built into OneSpace to start with. And then the last use case I wanted to talk about or just describe at the start here is the traditional, I say traditional because I've heard it, it's one of a long time, and it's one of the first things I've heard of, which is I want to keep data in multiple places, and you may have various policy reasons for this. I used to work at a company that had a requirement that all of their data was stored in two places that were at least 75 miles apart, in case there was some sort of weather event or something like that that made you completely lose one. But this would be the kind of thing is I want to keep data locally, but I also want to keep another copy in Amazon's cloud in Europe, and I'd like to keep another one in Google's cloud in Australia or something like that. It's something that's widely diverse, but also not the same. It's distinct in the data path so that you know that even if there's a bug in one system or one system goes down, that you still have access it into a whole different company, whole different data path, things like that. When you're writing the apps, this is something that ultimately you want because you don't want to have to deal with those fiddly bits of storage. You don't want to have to write your app to make sure it selectively puts it on all the right places. You don't want to have to make sure that you're handling the various errors that happen there. You don't want to have to write an app that has 14 different APIs in it to talk to whichever one of the 14 different endpoints you're going to be talking to. You just want to put your data someplace and let the storage system figure it out. So that's what gets us to OneSpace. Those are the kind of questions that OneSpace is trying to solve, has done some of these pretty well so far, and will continue to improve it for what's going on. So how does this work? From here, I kind of want to talk about the basic design of OneSpace, where we go, how it looks, and things like that. And then if the live demo gods are with us, I'll be able to show you very quick demos on that, and then we can have some questions. So to solve this multi-cloud problem, if anybody is solving these things, if you set out and write down on your whiteboard, what problems do we have to solve? What do we have to invent in order to solve these problems that I just described? Let's figure out what those are. The first thing, and I want to be clear about this up front, OneSpace is designed to run on top of and alongside Swift. So we kind of assume, and we have some assumptions in there for the time being, that there's some tight integration with Swift itself. I'll mention some ways that may be able to be abstracted in the future, but it is an important bit. We're talking about a Swift cluster, object storage that supports the Swift API, of course, and also the S3 API. Can be deployed globally, and then you can use OneSpace to enhance that and connect that with other clouds. So the first thing we need to know about when we're going to join multiple clouds together is what we would call a mapping. And a mapping has a few different key components. We've got two endpoints, which makes sense. We've got my local cloud, or cloud 1, and cloud 2 is my remote cloud someplace else. Only remote in the sense that it's not local, no distinction on physically where it is. You've got a direction that the data is going to flow. Am I pushing data to that? Or am I pulling data, or am I querying that other system and pulling it back in? We need to know how to talk to the other system, so we're going to have some credentials for that. And of course, what API are they speaking? And then we can do some interesting options on that transport itself. So it's not just a matter of there's a byte over there, and we want to put the byte over here, let's go pull it out, or vice versa, we can push it. What if we only wanted to do that at a certain time, or after 30 days, push this data over there? Or do we want to, what happens if somebody deletes it in one? Do you want to propagate those deletes back and forth so it's deleted everywhere? Or do you want to make sure that one is a never delete version? What about crazy new stuff that you could think about, like I want to translate the data as it's being pushed. I want to make sure that this movie is saved locally, but when I sync it over there, it's transcoded into some other format. That's kind of an interesting idea. Or do it based on a metadata policy. So I store 1 million cat pictures, and I want to only push the Siamese cat pictures with blue backgrounds over to the other side. Or I'm storing a bunch of medical records, and I want to make sure that I have a validation on every single bit of metadata such that I know that they have a record, a key value on their, the key on their metadata that says, here's the patient ID, and the patient ID conforms to a particular set of rules. We can enforce all of that things when we're in the data path. So the first thing we have to figure out is, what's that mapping look like between these two endpoints? That's the first problem we have to solve. Inside of OneSpace, that looks like this. There's a configuration file, it's JSON, and it stores these sort of things. This is just the sample config file from the project itself. We've got the account and the container, which are from Swift. We've got the AWS endpoints. We're going to push to S3 in this case, and we're going to say what the API endpoints are. We've got a protocol here we can say is in this case, we're going to use the Swift API. A few other things we're going to do there. You can see I've got my credentials as well. You'll see this in an actual real example in a little bit. So that's the first problem we have to solve, is the mapping. How do we describe each endpoint and the relation between them? Another problem is, I don't know the right way to say this other than there's some sort of cloud proxy sort of thing. Given that remote endpoint, how do you talk to it? And that's easy to start with. You say, oh, it's the S3 API, or it's the Swift API, or it's the Azure API, or it's a file system, or something like that. But what happens when the different endpoints don't support the same API? What happens there? How do you translate that? What about special features? Like object storage systems have generally a particular size limit for an object. And then they have a special, more different way to do big objects. But the way they do big objects are different between the different systems. And that's not even accounting for just the different subtle differences like the performance and the configuration sort of, you can request 10,000 from here, but 1,000 from there, and how do you do different paging and things like that. So you've got to worry about translating all of this. And these sort of cloud proxy things are not new. We've had libraries like libcloud and jcloud, Fog and Ruby, all kinds of stuff like that, that allows you to give some sort of common denominator inside for your application so that it can talk to any sort of cloud storage endpoint. And that's nice. And there's some interesting things that are out there. One project that I'll mention here that, in fact, OneSpace uses quite a bit for testing is something called S3 Proxy. It's actually been expanded to be a lot more than S3. But it's written by a gentleman named Andrew Gall. It's a great project, and it's great for our testing. We'd considered it incorporating it into OneSpace itself for various reasons that I won't go into. We chose not to for now. We use the cloud proxy that we use is really just using the Swift client that is part of the Swift project itself, and we're using Bodo as a Python library to talk to S3 endpoints, and being able to do the translation between there. So the important point about this is that this cloud proxy, this API translation, is really important because it comes back to the fact that you need to own your data. It's not about, I can put some binary blobs, and trust me, they're cat pictures, or whatever the case may be. The point is that you need to be able to, independently, out of band of anything else, still be able to talk to that data source and get your data back out of it. And so OneSpace is very, it's very important that OneSpace always stores something in the native format of whatever that target is. So if we're translating between Swift and S3, your data in Swift is a Swiftish object that would look just like that, especially when you're thinking about large objects and things like that. But when that's translated to S3, it's stored in S3 just like a well-behaved S3 client would do. And the same thing would apply as we build out integration with other storage systems. So that's nice. Those two things together, a API translation proxy, the mapping thing, help us solve one of the big problems of how do we move data back and forth. There's another problem we want to solve, which is the other big part of OneSpace, which is how do we unify those namespaces together? So remember some of those use cases where if I have a Swift cluster and an S3 cluster connected together, and I move some data between the two, and I ask for the data back in my Swift cluster, but it's been moved to S3, I still want to be able to get it back. I want to not have to rewrite my apps to talk to the different places. So the way we do this in 1space is with a piece of code that is middleware in the Swift proxy server. What that functionally does is that when a request comes in and tries to be served from the local Swift cluster, then if it's not there, it'll turn a 404 back. And the S3 shunt will, the 1space shunt will intercept that, detect that there's a 404, and say, that's actually mapped to another S3 bucket over there. Let me go fetch it from over there. And obviously, that's going to add latency and things like that. But the other hand is you get a unified namespace. So I did skip over one thing I want to talk about, which is, I said it was middleware in the Swift proxy server. What's that? Middleware is a way to insert code into the request and response pipeline. Swift is written in Python. It has something called a proxy server, which serves the API. And we have a lot of different things in the default middleware pipeline there. So the first one that we have is something called catch errors. And if there's anything that went wrong that wasn't handled by anything else, we'll catch it right there and present a pretty warning instead of a traceback to the clients. As we have logging and auth and things like that. So if we insert something in there, we insert our 1space shunt middleware, then we have the ability to intercept the request and the response and do something on that. So in this particular case, the request will come in, go all the way down to that proxy server. Oh, we got a 404. Let's come all the way back, tell that client that it was missing. And the shunt can say, no, wait, don't send them back that yet. Let's go ask for that in that remote cloud, and then we'll be able to get that response back and send it back to the client. And they will have then unified that namespace. So that obviously would add some latency. Those extra requests will add latency, the extra network time, depending on how far away those remote clusters are. But one of the options that you can configure on 1space is the ability to say, if you went and fetched that remotely, you can lazy load it back into the same cluster so that the subsequent request will be fast again because it will be local. So this piece of code, this shunt, is what does the namespace unification. That, combined with the ability to move data based on policy, is really, really powerful. So the next thing, so those are the two things. We've got the ability to move data based on policy, optionally do stuff to it as we move, and we've got the ability to unify multiple clouds into a single namespace. Those two things right there are pretty cool. But you'll notice in all of the things that I've said, I've kind of implied that the primary of the 1space is designed to abstract away a whole bunch of different clouds so the client doesn't have to worry about it. But everything I've talked about so far has said that the primary local thing is this on-premises Swift cluster. Well, that may not be the case all the time. So we need to figure out a way to truly make these a little more balanced, a little more equal within the overall storage infrastructure. So we've got this other piece of code that is called a cloud connector. And the cloud connector allows the same application to run in a remote cloud, compute-wise, and access the data that is either in that remote cloud or on your on-premises cloud. So I showed this picture earlier, but I want to talk about a little more detail of what this looks like. Remember, I talked about this when I was thinking about how do you do that cloud bursting sort of thing. How would you do analytics or rendering or transcoding or something like that based on somebody else's compute by still accessing this? The way this works is kind of like this. We've got our local cluster. That's where the primary data is. I don't want to share that data. I want to keep all of it as much as possible inside of my own firewalls, protected by my own policies, all of that sort of thing. But the cloud connector is a container that runs in another compute location. And it implements, right now, it implements an S3 API. It's a very, very, very stripped down piece, refactoring of the Swift proxy server. And it runs the S3 API. So you can talk to it just like you would talk to any other S3 API. And instead of trying to serve the data directly, it understands those mappings that are set up for 1space in the config files, and then is able to fetch it from S3. And if it's not there, it can then fetch it back from your on-premises storage. This is similar conceptually to the middleware, but it's kind of external to any one particular storage cluster, which is pretty good because obviously we can't insert code to be run on S3. Amazon is not going to let us do that, much less any of the other clouds. So you can kind of think of this as another little middleware piece, but it's external to one particular cluster. One of the interesting consequences of this design, imagine this. I have a lot of data. I want to, let's say we're going to transcode some movies. It's going to take a long time. We're going to have, we recorded 8K video, full frame recording, all that kind of stuff, and we need to put it down to all the different sizes that people can watch on the internet. It takes a lot of CPU to do that, and I'll do it all with my computers in my data center, inside of my firewall. But I can't keep up with those, but I could use EC2 spot instances. And those will be cheap overnight, but the problem is they have a nasty habit of just going away unexpectedly as somebody else decides to pay more money for them, which is fine, but I need to account for that in my application. I could say that each of those spot instances, as they're brought up, I need to figure out what their IP address is. I need to somehow programmatically figure out how to connect it back to my storage cluster on-prem, which great, I can give it the credentials and endpoints, but now I have to figure out the firewall network configuration settings. And have you ever tried to talk to a network or security people about, yeah, we've got some arbitrary things, they're running in EC2, they'll come and go, there may be 5 of them, there may be 5,000 of them, I don't know. Can you open up some firewall ports for them? Like, no, that's not gonna happen. So one of the things that this lets you do is use the cloud connector piece as the only authorized, you can run multiple of them, but that is the only authorized endpoint back inside of your network, which means that you can drastically enhance security about computing on your data that is in that public cloud, but you have access to the stuff that's on premises, and you only gave access to the known IPs that are running this Docker instance. So that's a really cool sort of thing. And that makes a lot of sense for a lot of people as being able to take advantage of a lot of multiple clouds, compute and storage, and still keeping a sane and reasonable security story for this. There's another piece that we've started working on. It's not quite ready yet, but this week I've been watching as the patches have been landing, called a NAS connector, which conceptually does something very similar as the cloud connector, but instead of saying abstracting a public cloud, it will be able to abstract away an existing traditional storage footprint. So imagine if you've got a bunch of NetApps or Isilons or other NAS boxes there, but you want to not have to migrate all of the data immediately off. Moving data is very, very slow and expensive. But you want to start spinning up your new cloud infrastructure. Your apps need to be written to use an object storage API. Yay! I've still got 5 petabytes of data on my old NAS boxes. How do I get access to those? So the idea of this is to be able to connect back to that and bring that traditional NAS storage into the exact same namespace that your cloud apps are already using. So that's an exciting new thing that's coming pretty soon. The last piece of how does this work is there's the question of how do we find work to do. There's a few ways to do this. Some of them are better than others, but the way that we do this right now is using a library we've put into a separate project. It's also open source, and it's called a container crawler. It is very Swift specific because it is designed to walk over drives inside of a Swift cluster and find some of the internal data structures that Swift knows about and yield those as here's some work items to do. And it does it in such a way that when you have multiple replicas of the data inside of Swift, it'll partition that out because it'll say we've got a bunch of different workers so we can know which things to immediately check, and then if we'll on the back end do it, check those other ones later so we don't miss anything. So we've got this thing called Container Crawler, which is a library that we import for some of the other work. But you can also think about some other ways that this would work. You could use things like notifications if that were available in Swift, or it is available in some other public cloud systems. You could get some notifications on that. You could get other sort of API calls to get to that, to find the list of work to do. So the basic point is that, to sum up on those, the basic questions you have to solve are, what are your mappings? How do you know what the endpoints are, what you do with the data transfer between them? How do you unify that namespace? How do you allow the apps to, how do you allow the apps to talk to any of those endpoints as a primary location. Kind of some ideas of doing that with more traditional storage instead of just the cloud storage. And then finally, how do you figure out the work items to do to kind of tie all that together? So that's kind of the basic overview of what 1space does, kind of some of the problems that people set out to solve when we were working on this initially, and then kind of some of the big questions that a solution to this has to do. And these are all, of course, things that 1space has implemented. So now the fun part. OK, so let's see what I can do here. I am going to, good, we've got this. I've got 3 tabs open. And I have, oh, here we go. No, let's not do a new version. Thank you. OK, so I've got this on, this tab right here is open to a Swift development environment. This is running in my office in San Francisco. It's a Swift all-in-one thing. Nope, reset Swift. OK, so we're going to clear everything out. We're going to erase everything. We're going to start over from scratch. And then we're going to start Swift up. OK, so that's going over there. Right here, I have another tab that's just locally on my desktop. And I have configured S3 commands to talk to S3. So I can, for example, see what buckets I have access to. And you'll notice the first 2 there are LCA test and LCA test 2. And then I have this other third tab open where we will be using curl to directly talk to a Swift cluster. So in this example, I'm going to see some of the server-side stuff. We're going to see the S3 API talking to real S3. And then we're going to see unifying that with 1space to my Swift all-in-one development environment that I have on a box in San Francisco. So here's how it works. Let's see. I'm going to go ahead and get some credentials for Swift. Can't type here today. There we go. Good. So I've got my request. And if you're not familiar with curl, this minus lowercase I will print out all the headers in the response. And I've got an auth token, which is how you authorize access to Swift itself. The storage domain here that I'm setting up, you notice I'm looking at this particular account, and I can start creating containers and objects inside of that. So let's look at the server side here. I've got a config file for 1space here. Those are very real S3 credentials, so I will be deleting them after this talk, now that they are publicly broadcast to the internet. But the important thing here is I want to show that we've got this synchronization profile set up. I'm going to map the test2 bucket into a Swift container called sync. I've got a migration profile set up over here where I've got the test bucket mapped to a container called from S3. So that is that. And just for fun, let's scroll that off the screen. Thank you. OK. So we will see that I will list out. I'm going to do the sync one first. So we're going to do test 2. And you can see that I have nothing in there, which is what I would expect. So that was set up with the sync container. So let's create a container called sync. And I'm going to put an object inside of it called O. Because I'm extremely creative when it comes to names. I'm going to put 4 bytes into it, 1, 2, 3, 4. And there we go. We got a success 201 created. And so we can look back inside of this container. We've got the object O. And if we looked at it there, you can see that I've got the object came out 1, 2, 3, 4. So yay, Swift works. That's good. You'll also notice that I don't have anything inside of S3 yet. So that's fine. But I will then run. There's 2 processes that I'm going to show you here. Obviously, on this Swift cluster, I have that shunt middleware installed and working. But I also, and we'll get to that when we get to the migration piece. There's 2 other processes that run in the background on the cluster here. There's the, currently, they're in the process of renaming this a little bit. There's the sync process, and then there's the migrator process. So we're going to look at the sync one first. And There it is. Okay, so, oh, that's the migrator. My history here. Okay, so we're going to give it the config file. I'm going to tell it to log to the console only at info level, because otherwise it'll scroll way off the screen and it'll be terrible for things here. So it's going to process things, and it's done its work, and it's going to go to sleep and then wake up a little bit and process it again. Well, now, if we looked at the Swift cluster again, my sync container, you'll find, oh no, there's nothing there. Actually, that's great, because the configuration parameters that I have on here say immediately move it and delete it locally. So in this case, anything that I'm going to, this almost becomes a Dropbox to S3. And then any data that I put inside of this local container called sync, it's going to be, as soon as that process runs in the background, it's going to push that to S3. So let's see if it actually worked. Please work. Ta-da! I've got an object there. Now, it's directory. That's kind of weird. What would that mean? Well, what we do here is we give things a prefix, because things like S3 don't allow you to go create 10 million containers like you could easily do in Swift. So it is entirely possible that if you are taking your local cluster from Swift and pushing that to S3, you're going to have to have some sort of pigeonhole problem and have to put a bunch of different data inside of the same bucket inside of S3. So we name this with, there's a little hash there that's at the beginning, and then you'll see that that looks like the account name. I'll go ahead and just show you that's also the container name in there. And inside of that, we have the object O, which is now 4 bytes long. And if we got that back, you'd see there's exactly the same 1, 2, 3, 4 bytes. So we have, if I, for example, created another object, and I was extremely creative and call it O2, and notice this thing's still running in the background, doing its thing. And I looked back in the listing of S3, you'll see that I have another object there called O2. So that's the sync. That's great. I'm going to go ahead and kill the sync process over here. Let's move on to look at the migrator process. So again, that goes into the LCA test bucket. This migrator process really can think of as sync as push, migrator as pull. And I'm going to put something into, here's what we're going to do. I am extremely lucky that I get to spend some time in New Zealand after this conference. So I have written up a little New Zealand schedule, so I'm going to put that in S3. And you can see it's now been uploaded. And if we looked at it, you'll see that it's listed there. Now, back to that configuration, the mapping for sync2 was mapped to the bucket from S3. I figured that would be a fairly obvious way to do it. So if I looked inside of my Swift cluster and decided to, from S3, do a listing on this container inside of Swift called from S3, notice it takes a little while. That's intentional. But look, I've got a New Zealand schedule there. Now here's some other interesting things about that. This is not locally in my cluster, and I'll prove it to you. First off, I'm going to do 2 different things to show you that. The data itself, I'm trying to access this, but instead of doing a read request, a full GET request, and showing you the headers, I'm simply going to do a head request and show the headers on that. The head request is a little bit different in that it gives you the exact same header response as a GET request, but it will not actually transfer the data itself. So in this case, we can see some interesting headers here. One, I was able to access this data and not get a 404. I was able to get a 200, it's fine. I noticed some things that S3 set when it was set up, and we noticed that it came from Swift itself because we've got these transaction IDs, which are part of every single Swift thing. But notice we've also got these remote XAMZ headers. These are things that came from S3 itself. So if we did the S3 thingy and looked at this remote request ID and all that kind of stuff, that's what it matters. And you notice this server ID says Amazon S3. That came from S3. And the other cool thing is, what if we don't want to do a head on every possible thing that we could do? So remember, we had this inside of the listing. That was a head request instead of a GET request. So we can actually do the request there. We see that comes from Swift there. Now watch this. Instead of doing a text-based listing, let's do format equals JSON, Python-m, JSON.tool. So I'm going to do the JSON listing of what's in there. Hide the header so it doesn't try to parse that as JSON, and this is what you get back out. So you get a listing as normal inside of Swift of here's the JSON stuff, but you notice there's a new field in there called content location, and this specifically says it is in S3, specifically the real S3 in a bucket called LCA test. So that's pretty cool. So that means that I can do a listing on my local Swift cluster and get a mix of stuff. For example, if I were to let's do this. Let's put an object inside of here. Let's call it local data binary, and we're going to be super creative, 56789. I'm going to make that a post request. Great, put that locally. You will notice this is not, hang on, this is not in S3. So we go back to S3, and we do a list on that bucket. We have one and only one thing inside of S3. Got this New Zealand schedule. And so, yep, that's it. Here's the JSON. There you go. You got this one right here. The New Zealand schedule comes there, but the other one does not have yet the content location, which means you know that it is local, and the name is local, in fact. Now, there's one other thing we haven't done yet, which is the whole point was to migrate all of this. So we can obviously set up parameters on how soon you want to migrate it and how and all that kind of stuff. So let's run the migrator. There's the migrator. We're going to output log level info of log level of info and throw it out to the console. And it's processing. It's doing its thing. It's finding data and sleeping and then doing it over and over and over again. So let's see what happened when we do this again. Look, it is in S3. It is also in Swift. So that's pretty cool, which means that if, for example, I were to fetch this again, where is it? There it is. We're just doing the head request on it. Notice that's a lot faster because it came from that device right there rather than having to intercept it and go out. So there's more we could talk about. There's more we could kind of demo, things like that. But that's the two things that I really wanted to show you, the kind of sync and the migration thing, how you can do that over time, how you can, the lazy load that comes back, and how that's put together. So that worked well enough. So that's where we are. If you want more information about 1space, you can go to 1space.io. That is the in-tree source docs that are built every hour and pushed out there. You can find the project on GitHub under the SwiftStack repo. I want to make an important point about that. Well, we'd love to have you come get involved. One of the things that we as a company, I work for SwiftStack, that has created 1space, contributes a huge amount to Swift and a few other open source projects. One of our firm beliefs is that if the data touches, if the code is in the data path, the data belongs to you, and that code should therefore be open source. We make our money by selling some proprietary management software on there, but the whole solution of storing the data and managing it is kind of what we put together. But we truly believe in making sure that people have equal access to their data wherever it is, and the best way to do that is with open source. There's a few other things we want to kind of work on in the future. I'd love your help on this. I mentioned the NAS connector. That's something that's being developed. We need to put that into production pretty soon. I'd love to put in Azure support. We've got a degree of ops metrics and monitoring and things like that. Love to continue to improve that, especially as other people have different experiences. Always the question is going to be performance. How do you reduce those latency times or get as minimal as possible? And the whole idea here, the promise, is really exciting to me. I mentioned some of this before, but when you're in the data path, you can start doing some really interesting things, and 1space allows you to do that. Transcoding, translation, what happens if we did a text file and translated it to French when we put it to a foreign cloud in OVH in Europe? That would be amazing. What happened if we validate the metadata on everything as we're doing it real time? Do audio I don't know, if you're in the data path, you can do some really amazing things. And what 1space allows you to do is take ownership of your data regardless of where in the cloud that is. So all that being said, I don't know if I have any time for questions or not. Not really. Okay, if you have questions, please find me afterwards, and thank you for your time.